I'm Lars. There. So, a short introduction, perhaps. My name is Lars Ershammar. I work as a system engineer here at Cisco, Sweden, at our data center office. So I work with everything that concerns the Cisco data center portfolio. And that includes the Nexus area for switching, the MDS for sound switching, UCS for computing, and now some of the software we have, and also the ACI concept that we recently introduced.
Yeah, and I am Bob. I work for the CTO office, Cisco, where there's a team that works on OpenStack, focus on the community side, and we're going towards internal different business development teams from this very product.
So, some agenda here. We get a short introduction on how Cisco works with OpenStack and what we're using it for, and some of the background. Then Bob here is going to talk a little bit about Neutron and Nexus 1000B virtual switch and the virtual router and how they're being implemented in OpenStack. And then we're going to show a demo. And then later on, we're going to talk a little bit about the ACI concepts and how we extend those into OpenStack and Neutron APIs.
You share the slides of yours.
Sure. So, I work in sales mostly. That means that I go out to customers and they ask me for 2 or 3 things. I need my IT infrastructure to be simpler. And Cisco is a networking company mostly, or we're most famous for that. That means somehow, somewhere along the way, networking got complicated. That means we have ports, IP addresses, MAC addresses, and so on. These things mean a lot for networking people, but they don't mean very much to someone that does not speak the networking language. Also, in the IT infrastructure today, you need agility. With that, I need my infrastructure today or yesterday. That's the great concept of cloud. That's what Amazon got such a huge market so quickly. Because when a developer said, I want my virtual machine now, not in 3 weeks. So customers ask, can you fix this, please? And here's where OpenStack comes in. At Cisco, we have the community, where Bob, among others, work, where we try and work some on the code for Neutron and other services. And we also have Lou Tucker, that is our CTO for cloud. He's in the chairboard at the foundation, right? We also have an open source Cisco OpenStack installer that you can go to the website and download and try it out. That is optimized for the UCS and the Cisco services. And then we have a commercial part, of course. Cisco is a company. So here at that site, to visit, and you can download the Cisco OpenStack installer. It's make life a little bit easier if you have UCS or the Nexus platform for networking and computing. If you want to try out OpenStack with the plugins, not having to install them manually. So, anybody familiar with WebEx, the service for telepresence or something like that? Yeah. Cisco runs WebEx on OpenStack. Basically, we have a lot of internal things that now. We used to be a complete VMware shop. Now we're seeing internally how we're migrating from VMware to OpenStack internally. And not only that, some of the services that we are going to be offering, say for example, if you're a student and you want to try out and build advanced networking, if you want to take your CCIE classes in your certification, normally you would have to acquire some perhaps expensive hardware to try it out, to get a lab. With OpenStack, and we're going to have to virtualize some of their networking platforms, you're going to be able to build and order those images on the fly. So you can build a logical topology with the services that we have them. So say, for example, I want to have a CSR, I want to have an ASA firewall, I want to have an ASR 1000 server or router. You can order them and they're going to pop up just like that. Of course, they're virtual, but you can actually train with them. So it's going to be, have someone to use packet tracer here. Yeah, it's going to be that on crack, basically. Sure, question.
Is it like GNSP?
Yeah, the difference here is it's actually official builds from Cisco, and it's going to be our complete portfolio range. It's going to be hosted on our side of the cloud. So you just can, just like Amazon basically, but just for our services.
Free?
For students, yes. For commercial, no. That's what I heard, at least yesterday. That might change. So, how many of you are familiar with the concept network function virtualization, or short NFV for sure? Yeah, it's the same thing here. Principle is the same thing. You're trying to have those ordinary hardware boxes, those hardware appliances. Some got fed up, or some are not, ideal to have in hardware boxes. Those services can actually be virtualized. So if you're in a mobility service, you can have a GGSN or SGSN if you're in mobility. If you are with a videoscape, if you have like Netflix that kind of things, if you're a TV4 or whatever, you can have the back end virtualized. So instead of scaling up, buying bigger boxes, you can scale out with adding virtual machines. So these kind of things, these network appliances, can run a standard Cisco UCS x86 servers. These are some of the functions that Cisco are developing for OpenStack as we speak. So Cisco has three ways. We see VMware as partners, Microsoft, and then we use OpenStack. Oh.
Yes. So this, you can see this as the second leg of this presentation, and it's supposed to, I don't know, how many are familiar with Neutron, the networking? Okay, so it's not everybody at least, so that makes sense. My plan is to go through some of sort of explain what Neutron is, so how it's, what are the components of it, and then bring up some of the new things that are being worked on, and also show the demo. So Neutron, which used to be called Quantum, but there was some clash with name, so it transformed into, got the new name, which is Neutron, and it's now a core service within the stack. Became part of it. I think it was more recently, and it is sort of networking for the other cloud services in OpenStack, but also for users directly. So it allows you to create networks. Actually, there are two networks, ports on them that plug things in, and you get connectivity that way. But it also has a broader range of abstractions that have been used, like security groups and also more advanced services like load balancers. So I will come back to that. And the whole reason why Neutron came to was basically that from the very beginning there was networking, because obviously networking in Sweden is tough, but that networking was part of Nova. And so early on it was sort of identified that it's very much geared to a select set of use cases. And it wasn't so easy to support other types of use cases, more advanced network topologies and so on. And also there was a lot of interest from vendors of this, and they want to be able to easily integrate their equipment and their technology into this. And it was also deemed that Nova networking was not quite suitable for that. It was better to start fresh. And also in general to foster innovation, make things go. So with Neutron, you can create more advanced topologies. You have multi-tenancy and all that stuff right from the cloud. So you can support, for instance, like tiered topologies where you have a front end, a middle layer, and the database back. So roughly, if you look at Neutron, as I said, it is supposed to be able to support a wide range of use cases, but also make it easy to integrate new technologies. So that has led to a plugin-based architecture. That was the choice then fairly early on. So basically, there is the Neutron API server, which is the one that sort of processes the API and provides sort of expose the northbound API towards the user as the REST API. Then you specify or you load a core plugin, which is the one that will actually make sure that those primitives that are exposed to the user actually get implemented, transformed into real things that can move packets around. So the Neutron plugins are the ones that talk to physical devices, virtual switches, or software controllers, and all the things. Depends on it's basically up to any vendor to come up with and choose how this part looks. And then there's a set of APIs between the server and the other plugin interact. And obviously, there's a database to store all this information. That's where you have the persistence status. So Neutron has a core API, with basic set of primitives, with subnets, networks, ports, and subnets, basically. And then vendors and users may want to expand this or grow this API, expose more functionality. And in Neutron, you do that by extensions. You define an extension, and that essentially defines new resources. Layer 3 and routing is one such extension, which expose two resources, routers and floating IPs. That by defining an extension, you have the ability to expose it towards the users. And then a plugin can choose to implement one or several of these extensions to make sure that something actually happens when the user calls or uses those REST API functions. This was rarely seen. Is this visible at all?
No.
It looks nice on the screen. So there has been a formidable explosion of these. So some plugins have a long list of extensions. So probably something. The intention is really when an extension has been sort of adopted by essentially all plugins, then that API should really migrate into the core API. That has not happened in reality, but this is where it is.
So plugins are separated from like the mechanism driver and type drivers. They don't have.
Well, the mechanism driver and type driver, that's part of the ML2 plugin, which is one of it's the most recent or one of the more recent free and open plugins. So it's really it's a construct within that plugin only.
Okay, so that's the separation.
So type is the type type is sort of that you have different. It can be VLAN, GRE, and XLAN, and so on. And then the mechanism driver is the vendors or how you actually realize that type. I wasn't going to talk about the M2. So from the beginning there were the core plugins, and that was it. But then after a while there was an interest to introduce and support advanced services or other services than the basic one. And that led to the introduction of what is called service plugin. And a service plugin is really not different from a core plugin, because it's just loaded in a slightly different way and does not expose the sort of the basic constructs. So the first one to be introduced was the load balancer as a service plugin, and they decided, the folks that were working on that decided to go for a driver-based plugin architecture. So you have one load balancer plugin, and then different vendors can make drivers to get into that. This is by no means like a necessity. You can, you could produce a separate load balancer plugin if you want. But since then, the VPN and firewall that have more recently been produced, they have also gone down the lane of using drivers. But that's just a choice. One can easily write a separate load balancer plugin for firewall. Now, for the idea in OpenStack and Neutron is that there should be a free and open implementation that anyone can use without having to buy special products. And in terms of Neutron, the free plugins used to be the OpenVSwitch plugin, the Linux bridge, and M2 came in and supposed to take over that role. And OpenVSwitch and Linux bridge are supposed to be deprecated. But these free plugins, basically, the anatomy of them are pretty much what you can see here. There is the core plugin, and that does the basic API handling and database interactions. And then to actually create the networks, be it GRE tunnels or VLAN-based networks, there is a plugin agent that runs on each compute node. So the plugin talks to the plugin agent via message queue and tell him, well, now a network has been created or something like that. Then for routing, or for IP addressing, there is a DHCP agent that creates namespaces and handouts IP addresses for the different networks. And finally, there is a L3 agent, which is creating virtual routing systems. That's basically a fast run through of Neutron. Actually, I was going to let you talk about
it. So, normally Cisco produces hardware, Nexus devices, and catalysts, and so on. But for a few years ago, we created the first virtual switch, and that was the Nexus 1000V. Nexus 1000 is a virtual switch. It runs on a normal standard x86 server within the hypervisor. So if you look at the topology, the network topology, on the left side, you see how the VMs and the hypervisor, all the traffic, network traffic, goes out of the leaf switch and back. In the right side, if you use a Nexus 1000, you can actually have another layer of switching. So you can have the VMs can switch within the server without going out onto the physical switches. So here you can see a closer look at the server and the hypervisor, and the VM is a virtual Ethernet module. It's the data plane of a switch. So the Nexus 1000 is separated in a control plane and a data plane, basically. The Ethernet module is the data plane for the packet forwarding. And the VSM, virtual supervisor module, is the control plane. So you can have several VEMs. So if you can have up to 128 Ethernet modules over different servers controlled by one supervisor module. Does anybody recognize the definition or the Wikipedia definition of SDN, the separation of control plane and data plane? This is an early version of that. So another ingredient we need to talk a little bit about, VXLAN, is an extension, or should I say, an evolution of VLANs. Traditionally, in a data center, you have a lot of stretched VLANs. Normally, some enterprise customers have multiple data center sites across distances. And normally, for server virtualization, you need to stretch the VLANs. And that became an obvious problem in the long run. So this could be one way of separating the networking in a data center. The problem with this kind of separation, where each rack in a server or in a data center gets one layer 2 domain, is that if one customer buys up all the servers in one rack and needs more capacity, you end up with stretched VLANs or something else that's not particularly nice. So the answer is VXLAN. It's basically a routed layer 2 thing, protocol. For an example, here are the servers with a hypervisor, and then you have the virtual Ethernet modules with Nexus 1000. And here's your physical standard networking equipment and your network. With VXLAN, you can basically build an overlay network, a virtualized network. And then we can set up connections, or should I say, bridges or tunnels between our virtual machines in the data center. Meaning we can have, on the physical side, we can have a purely IP routed network, ISIS, OSPF, and so on, without having to extend to having stretched VLANs. So you only need to pay the layer 2 price when you really need to. Like this. So you think about all these physical networking elements as layer 3. Then you build logical layer 2 topologies over that IP space.
So you rebuild the tunnel in the Nexus 1000?
Yeah. And the control plane, the supervisor module, sets up those bridges, basically, tunnels. I think it's yours.
Is it? Yeah.
I'm not taking too much.
There is a plugin these days for the Nexus 1000 in Neutron. So it's basically the N1K originally was for the ESX and VMware environment, but now there is a version of it that runs with KVM, so commenting for OpenStack. So you can now essentially use the N1K solution as in Neutron. Use that as your virtual switch. Supports VLAN and VXLAN. It's been used together with the original Cisco plugin that was in there from very early on. That is interacting with the Nexus top of rack and hardware switches, so that you can, for instance, if you use VLAN mode, you can have you can get VLANs configured on your hardware devices and top of rack switches, so automatically. Another nice feature that the N1K has, which is, as far as I know, no other plugin right now supports that, and that is VLAN trunks all the way up to the VM. You can aggregate multiple networks and get them to reach a VM. And this is a very useful feature if you're going to support the things with the VM. I'll get back to this. There's also some of these features in the or configurations of the MFK is visible in the OpenStack dashboard. So this is then leads me to the next thing here, which is what the bulk of this will be about, and also the demonstration, and that is the use of virtual machines to implement these services that I talked about, the service plugin. So in the Neutron terminology, advanced services is basically anything which is not sort of the basic traditional core services, I would say. So it's load balancer as a service, firewall as a service, and so on. Those are all examples of this. And there are some rather preliminary implementations so far, especially in the case of firewall and VPN, being much worked on. But right now, both of these types of services are the way they are inserted, because you create a VPN resource that you are going to use, and then it sort of needs to be somehow injected into the traffic flow and traffic path. And the way this is currently done, and the only sort of insertion mode that is supported is the routed or embedded insertion mode. So when you create a VPN resource set, you associate it with the neutron router, so it sort of lives in the neutron router. That makes the routers kind of important for this. And when an obvious sort of way of implementing these advanced services is by using virtual appliances, for which there has been a lot of products out these days, virtual routers, virtual firewalls, and so on and so forth. Oftentimes they are capable of doing a whole range of different services. And why this is attractive is, of course, that it's easy to scale and multi-tenancy and so on. Why does it say gateway? It's not supposed to say gateway. So there's a lot of interest to be able to use VMs to implement these services that Neutron provides. That's what, if you follow sort of emails or some of the blueprints and so on, there's talk about service VMs. That's really using VMs managed by Nova to implement APIs provided by Neutron. Just as from Cisco, I have to give one example of one of these appliances. The CSR 1000 is such an example. It's really an iOS. It's an
ESR 1000.
ASR 1000 physical router, but in a virtual form. That's pretty much the same functionality. It runs iOS XE, but in a VM, and it can do routing, VPN, MPLS, a lot of things. And it runs on KVM, so it's one example of one of these services, or what could be a service. So, based on what I just told you about the interest on service VMs and the way that the router is sort of currently at least at being insertion, then that led us to look into, okay, how can we implement the Neutron layer 3 routing API using service VMs? That's what I'm going to talk about. And to me, I haven't been so often this, so this was the first thing I did. And I was very, well, this cannot be too hard. But I was wrong. For those who are not familiar with what the routing API is, it basically provides two resources, router and floating IP. The router does exactly what you think about it. You can create a resource like this. You can connect it to a neutron subnet, and then it will forward packets by routing. You can also connect one of these routers to something called external network. And then this router can act as a gateway to the outside world. When you have one of these gateway routers, you can create the floating IPs. And a floating IP is basically an IP from this external network that is mapped to a private IP belonging to a VM to a NAT, one-to-one NAT station. This way you can expose or make this VM reachable from the outside. There is also a dynamic netting going on from the inside out by default. That's also part of the API. Then you have these common basic REST API functions: create, update, delete, and then set and clear the gateway and add, delete. That's the neutron routing API. That's what there is a reference implementation for that. Remember I talked about these open free plugins. So there is a reference implementation for this routing too. It's basically, it's the plugin. It can be a separate service plugin, or it's part of the core plugin. You basically get a set of functions to mix into that, which will make it allow you to create and update and delete these routers. And then when you have created the router, they need to be instantiated. That's where the L3 agent comes in. When a user has created a logical router, it actually corresponds to a Linux network namespace on networking, a dedicated node where this L3 agent runs. So the logical route is a network namespace. So basically, when a user creates a router, some things happen here, and then there's a scheduler here that will decide where should this router live, and make schedule decision, and then there's an RPC going on, and finally the namespace is created and gone. This is what is there in the just to use. So it kind of looks, I mean, there's a scheduler quite useful to say to create a VM and so on. Yes.
It's not ED.
But
ED.
no, it doesn't. It allows you to create set routes, static routes, but the dynamic routing protocols and things like that are not supported. Yes, it's being talked about, especially in the context of ED. But yeah, it was discussed.
Lower level routing idea.
No, if you want that kind of control these days, currently you need to essentially deploy your own VM and go do it separately from outside not use the neutron API, but rather you spin up a VM like Nova.
Yeah.
Okay, so there is this, and kind of sort of useful things that one would think one could use to do the routing in a VM. So instead of having this, we would like to have a VM do the actual routing. The only problem with the going from the existing implementation is that it's really very geared towards these namespaces. And the scheduler, which is a nice thing to have, the problem is that it schedules from these logical routers to an L3, that's sort of the things it operates on. So there is no sort of VM notion there. And the L3 agent, it really only knows to configure namespaces on the local machine. If it's a VM, then the VM will run probably somewhere else. The L3 agent doesn't really lend itself to do that, as it is now. So the current sort of open implementation is really much based on the assumption that the one that hosts this logical router is the same thing as the one that sort of configures it. And there is no support in Neutron itself then to handle this. And also to deal with the fact that if you want to create a namespace that happens like this, if you're going to boot a VM, it might take several minutes. So what we've been working on and what we've been doing is that we try to fill in some of these blanks. And one of the things we introduced then in the work was the notion of hosting entities and hosting devices. The thing where you're going to place your logical router. It can be a physical device, obviously the interest to Cisco, or it could be one of these service VMs. So that was one piece that was identified as necessary to have. And then if we talk about VMs, then we need something to manage them. We want to use Nova to actually start them and do all of that, but these VMs and these things, they need to be managed beyond what Nova can achieve. You need to be able to detect if one has it completed booting, and when should we create another VM, when should we remove one, and so on. All that kind of life cycle management of the VMs needs new functionality. Then the scheduler needs to be a bit more evolved, so that we can schedule from a logical router to one of these hosting devices that are part of some pool. And finally, when we have picked one of them to host it, something needs to go into this machine or router VM and apply configuration. So we have created a separate agent that has support for different drivers, because these are all different, and which can do remote configuration and some other things with machines that stop working. When we look at sort of logical routers and how you work with these resources, two very important actions are you plug it into networks and you unplug it from networks. And this is very easy in namespaces. When you introduce a VM, well, you have one option is to do diff hop plugging. You create a virtual interface. Yeah. Not all operating systems support it. And also the number of virtual interfaces that you can have is limited by the number of PCI devices. Many use cases, that's not a limitation, but I know that some use cases require like hundreds of games essentially. And that's beyond what you're used to. So this is where this trunking capability that the N1K has comes in very handy. Because now we can essentially just create a router, VM, a diff, and then when we're going to attach it to a network, we just add another network to be trunked on that diff. And when that network is attached, we remove that from the diff trunk. So this is something, right now it's only the N1K that has this. Sometime, not too far distant future, other plugins like the ML2 will have it too. And it was discussed at the last time. There's a lot of interest there. And it's very useful for this kind of.
And for catalysts, or is the rule out?
Well, this is on the virtual switch. So it's really when you connect a VM with a virtual switch. So in the hardware case, you don't have the same problem quite, but you still need to untag and tag, but it's a slightly different. That kind of trunking and plugging is also one use case, but it's slightly different. but that kind of being able to give, doing what you want to do is also being discussed. One of the yeah, and in the case of VLANs, VXLANs, then those can be mapped into a link local VLAN, in case so that the router or the VM only needs to know about VLAN. Okay. So what happens then if we are going to create a router that lives in a VM? So a user creates a requests a route and goes into the API server and finally ends up in the Python function in the plugin. Some database operations happen to register this logical router. And the scheduler does some work to decide, can this be placed into one of the running VMs, or do I need to create a new one? So if, let's say now that a new one has been identified to be needed, then the service manager will kick in and talk to Nova, which is the compute service in OpenStack, and ask it to spin up a new router service VM. And Nova will do that together with Glance in service and so on. Finally, a VM will boot.
And where is Cinder or Swift in this image?
It's not in this picture right now.
But it's used.
No, we don't use it actually. In our, at least in the cases we haven't had required any additional storage. Right.
And where the images are?
They are stored in Glance. Okay, I mean, okay. Or yes, they could be. Glance could in turn be using storage service from the case already. That's true. But yeah, I didn't. Probably there is some backend to this. But that's not visible or this. Yeah. Anyway, after this has essentially been dispatched, the plugin will talk to the L3 agent to tell it that, hey, there's work for you to do. There's a router for you to configure, and then the config agent here will based on information it gets from that one, will contact the router VM, and in our case, a logical router maps into a VRF inside itself. So it will create this VRF by configuration using a variety of protocols, depending on the version.
Yes. The CTA, is that the proprietor or is it?
Well, it is something we have done, but it's nothing of this is yet upstream. But it's not going to be closed in the sense that it's going to hopefully end up in the neutron poetry.
Yeah, I was thinking if we can use that for stuff that is not related to OpenStack. But maybe it's only for.
Well, in a way you could, I guess. Possibly. Would require, I mean, yeah, as a building block, possibly. Okay. So we have reached the point of a small pause in the lower slide. So what I will show you hopefully is that we can route using service. This is a kind of oh, I quit too early. Sorry, there was one more slide. So what I will show you, I will have two dashboard windows here. This is the one for the user, the one that's using OpenStack. It's in the demo tenant. And I've created a topology like this. I have two networks, both testnet 1 and 2. And I also have an external network. This is all sitting inside our lab behind a very fat firewall. So the connectivity outside is a bit hampered. So therefore I have a machine dedicated on this external network, and this is the internet. And I have two regular serious small VMs that we can use to send traffic. And then we have the almighty optical neutron router here. And hopefully it will forward traffic when you tell it to forward traffic. And it's a rather small OpenStack setup. It's all running on a single node. So we have the usual suspects here. And when it comes to Neutron, we're running the M1K plugin in VLAN mode in there. That doesn't matter, just one node. So there is a VSM. It runs as a VM. That's sort of when we install things, you get it. And then inside the kernel, there is a VM in the back. Yes.
What was the VSM?
This is the forwarding plane, and this is the sort of the controller goes to there. So the plugin talks to this one using REST API. That's how the plugin works. Because this M1K has a REST API. Okay. Why don't you see this? Yeah, so this is the one. This is the dashboard for the demo tenant, where I'm logging as a regular user, the way you're supposed to. I have see here that I have two instances running just here. And the network I mentioned. There are no routers here. So this is the topology. This one obviously cannot be in there. It's just to users. Ping 10 0 12 3. 12 3 is the other one. Doesn't work. But I have some connectivity. There's a DHCP. Oh. There's a DHCP server. That one obviously. So there's something there. See. This is what I meant. It's not the most. You have to live with this kind of jumping back and forth, but it's kind of. I slow down. Yes, okay. So I can also just briefly also show you, I mentioned that there were some add-ons for the dashboard for the M1K plugin. So I'm logged in as an admin in this case. And when you are logged in as an admin and use the M1K plugin, you get another tab here, which lets you see network profiles sort of this overview on what it is. But you can define profiles for network, and those things are sort of visible here. Created. There are also policy profiles that you use when you create ports. Those at the moment they are not. You can only see them, but you cannot edit. Okay. So let's try to create a router then. You feel the sensation? That will be nothing more fancy than and just using the Neutron API, just doing it in a different way. There's a lot of things happening here, but it's like, okay, very hard to show. But what happened now is that the request came into the plugin, and then the scheduler, it did the database operations, and the scheduler kicked in. It looked in the its pool and inventory of hosting devices, and selected a suitable one to host this. And this is, if you do this the namespace way, it is this fast. If you do it with a VM and you're going to boot that VM, then it can take like 3 to 5 to 7 to 10 minutes, depending on which kind of VM you're running. That's kind of not so attractive. So that's why this VM lifecycle management kicks in, because we keep resources in a pool that operates independently, so it can spawn new VMs in the background, so that you can essentially hide this delay that would actually otherwise happen. Let's now add an interface. Test. So I connect it now to one of these subnets. And if we go into the network topology now, you see that there. Hopefully, you'll be able to think. That router has 11.1. Isn't this so interesting?
Was it the right machine?
I think so.
From the right machine?
I ran this before that.
Check your icon.
Aren't you 12?
I can check the actual route. Maybe I need to check if that is config agent one. Look the other way.
You could take the break now if you want and continue afterwards. But it's up to you to decide.
Yeah, actually we can do that.
Okay, so let's take a 15-minute
So I can
break.
fix it.
And we meet here at 7:15 sharp.
You can